So our next speaker is Zoltán Simon, who will talk about time evolution simulation of the quantum mechanical wave functions in 3D spaces. And I'm giving the stage for you.
Thank you very much. Hi, everyone. I'm Zoltán Simon, and I'm a computer engineering master's student at the Budapest University of Technology and Economics under the supervision of Dr. Balázs Csépaly from the university, and also Dr. Péter Rancsó and Dr. Géza István Márk from the Department of Nanostructures of the Institute of Technical Physics and Material Sciences. Sorry. Their research is mainly aimed at carbon nanostructures, and you can find out about this research more in this website. In my presentation, I would like to briefly introduce to you wave packet dynamics, then tell you about two different calculation methods, numerical simulation methods, and also talk about the visualization techniques used to visualize 3D data sets, and then, of course, present the visual results. So what is wave packet dynamics? It's a methodology where you take a well-localized wave function and let it evolve in an arbitrary physical system. And then, of course, the scattering is dependent on the content of this physical system. And in this animation, you can see the evolution of this wave packet in purple. And a good thing about wave packets is that it bridges the gap between classical physics and quantum mechanics, because wave packets can bounce back from potential walls or slide down on potential slides, similarly to little balls. But they also, of course, exhibit all the quantum mechanical properties, such as tunneling, self-interference, and so on. In the research center, they already used numerical methods to calculate wave packet dynamics, but they only use solely the CPU of the computer. So I aimed to port the simulation to the GPU, thus leveraging the massive parallelization capabilities of the modern GPU architectures. And also they visualize the resulting probability spatial dimensions and also the time dimension. Now, here you can see the well-known Schrödinger equation, which is the governing equation of motion of quantum mechanics. Here I substituted the Hamiltonian operator for conservative force fields, where the red part is the kinematic operator, and the green part is the potential operator. The most interesting part is that the Laplace operator, which will cause a lot of problems in the future in this topic. And here's the formal solution of the equation. And by reparameterizing this equation, you arrive to the formula for the discretized simulation of the state of the wave function for a short delta t time period. From a previous time step to arrive to the next wave function. How to do this? Because how to calculate it? Because in general case, this is complicated to deal with this equation basically, and analytical solutions are obviously only available for very simple cases. So you have to use some sort of numeric approach, calculation. So in the literature, there are basically two big approaches, or different approaches. One is using the Fourier transformation to simplify the calculation of the Laplace operator. And the other group of simulation methods is the finite difference time domain methods, which these methods calculate the Laplace operator in real space by some convolution filtering. Now about the Fourier method. Well, the Fourier transformation has the nice property that if you Fourier transform a derivative of a function, it equals to the I times k times the Fourier transform of the original function, where I is the imaginary unit and k is the wave number. And for the Laplace operator, of course, we need the second order derivative. So we multiply by minus k squared. Okay, there is that. But also, you already have seen that with the Hamiltonian operator has the kinetic operator and the potential operator, and these two do not commute in the general case. And from this, you cannot really factor these to two terms, but we do it anyways, and we introduce an error of the approximation, which is ordo delta t cubed. And now we have separated the operator into three different terms. Well, okay, the first and the last term is the same, which only contains the kinetic operator, and the middle one only contains the potential operator. So we are almost done, and we are actually done because now the calculation method to calculate the next the wave function of the next time step is as follows. So you Fourier transform the wave function, then multiply by this term, which can be seen in the slide in Fourier space, then inverse Fourier transform. Then in real space, you multiply by the term containing only the potential function. This is a localized potential function in space. And of course, for the last term, you repeat the first three steps. And you iterate over this many times to evolve your state. I would also like to introduce a different approach. This is from the other group of simulation methods, from the finite difference in time domain approaches. Here, you take the power series expansion of the time evolution operator, which can be written as a sum, infinite sum of these sk terms. These are expanded like this. And here also the first or the zeroth index term is the previous wave function. And if we write out the Hamiltonian, you can see that now the Laplace operator is only affecting the previous this previous term, and also it's multiplied by the wave function. So this can be nicely implemented on the computer as an iteration. And of course, we cannot do it for infinite terms, but you do this step for, let's say, a p order of approximation of p. But there's a problem with this. Finite difference time domain methods are usually not so stable, and they diverge. So here I plotted the integral of the probability density for the visualized volume. That is the probability of the particle being found in this volume, and you can see p-values, the probability diverges, which is of course this is not right because probability shouldn't be greater than 1. And also the SOF curve is the curve of the Fourier method. You can see that there is a discrepancy between the p equals 10 and the Fourier method curve. This must be investigated further. but and also the fall off is because it left the visualized volume, so then it wasn't in the volume anyways. Now I would like to talk about the visualization techniques, which was a big part of my work, because I come from computer graphics background, so I did everything to make the visualizations as nice as possible. So far we mentioned that we simulate the wave function, which is a complex function, but usually they visualize the probability density calculated from this, so the square of the absolute value of the wave function. And also the simulation is carried out on a discretized grid of voxels. And you can visualize it using any volumetric visualization technique, such as isosurface, but here I use translucent volume rendering using ray marching. So you shoot virtual rays from a virtual camera, and you step along this ray and sample the data set. You apply some arbitrary transfer function to obtain the colors, and then plot this color on the screen. And also you calculate the attenuation of the volume. I went further and introduced some other techniques, such as coloring based on the phase. Well, wave functions are complex valued, so you can map colors to the visualization based on the phase of the function at a given position, which is also gives much more insight into the state of the wave function, which is always a good thing. Then shadows, it seems like unnecessary thing, but the human brain really appreciates if you give it more points of interest and things where it can interpret it more like a actual 3D image. Of course, it's, at the end of the day, it's just a 2D image, but you want to do everything to make it more comprehensible. And translucency is also interesting because you can use it to convey the information that, for example, in this case, sorry, I can maybe move this out of the way. That this potential wall has different potential values in different places. So where the potential is low enough, the visualization can be translucent. And I'm talking about this because I think these ideas can be applied generally for data visualization, of course. But I think this is important. Also, specular highlights. These convey that data. Of course, this is just a cloud of different values in a volume, but you can make it look like it's a surface by calculating the gradient of the data. We are calculating the gradient based on the probability density. Then this gradient can be viewed as the inverse of the surface normal. So you multiply the gradient by -1 and normalize it. You obtain some sort of approximation of a normal vector of a surface, and then you can use this to input into the any bidirectional ray distribution function and calculate reflections and specular highlights. Okay, my implementation is done using Python, and for the calculations on the GPU, I use the CUDA toolkit, and also I use NumPy and QPy. And for the visualization part, I use VisPy. I implemented a few custom CUDA kernels for example, for the initialization of the potential, and also to do the power series expansion method. And for the ray marching, a custom GLSR shader, which is the shading language of also of OpenGL and these languages. The project can be found on GitHub. With this all, I achieved a speed up of 50 times. So 50 times speed up as compared to the CPU implementation. Here I listed a few more details about the speed ups. Yes, so this 50 times speed up is for the 512 cubed size or resolution. There's that, and for as a benchmark, we use the double slit experiment to visualize this. Sorry for it's not running smoothly through the Zoom share. So here you can see as the wave packet is scattering when going through a double slit. This is a simple example which can be calculated analytically, and thus it can be we can validate the simulation that it runs right, and we did it. And one more animation here. I also implemented that the potential can be changed dynamically throughout the simulation. And well, this is just a benchmark to showcase this function, but this can be useful for example, for simulation of lasers and any dynamically changing potential fields. Here's a different visualization of the same simulation. To conclude, I implemented different numerical methods to simulate to calculate wave packet dynamics on the GPU, and this allowed us to make these simulations much faster than the previously used ones in the research center. And I also implemented various visualization techniques to enhance the comprehensibility of the data. From now on, we would like to continue this development, and also arrive to the state where we can actually simulate multiple particles, because a single particle is not always that useful to simulate, and in more advanced cases it would be nice to have a simulation which can handle multiple particles at the same time in 3D space, of course. Thank you for your attention.
So again, is there any question?
Very nice presentation. I would like to ask whether it's possible to use the scattering of two wave packets. Can you simulate that? So when you don't have a box or a split or whatever, but you have the two bunching, colliding wave packets. Mm-hmm. Is it possible to do that?
Thank you for the question. The short answer, in 3D space, it's too computationally expensive. Because for two particles in 3D space, you would require 6 dimensions at least in the naive approach. But we already did it with one-dimensional particles. And that way you can also simulate 3 particles, because you have the three dimensions, which are usually used for the one three-dimensional particle, but it can be also reinterpreted as the abstract simulation space of 3 one-dimensional particles. So in that, now I don't have, or I don't think that I have these animations here. Sorry for. I should have prepared that as well. Anyways, the important thing is that yes, then you can actually see how these particles collide and bounce back and so forth.
So as far as I understood, this is rather a computational
Yes.
question. So if
yes,
you
it's
can
expensive.
have access to larger facility or whatever, then you
it might
you-
be possible. Yes.
I think it would be a good
Yeah.
idea to move to this direction because there's a large community working on this either from the ELI or in the optical information technology, quantum optical things. So
Mm.
you
Thank you for
you
your
can have
suggestion.
very good friends easily.
Thank you. Thank you very much.
Thank you.
Is there any other question? Then if none, I see no hands, then we're moving on to our next talk, which will be from raster grid. So for our first industrial presenters.